Hello again. We're going to start looking at quadrilaterals in the next few videos. So this document, if you'll look at the tabs with me here, I'm going to split into 3 videos. The first, I will talk about irregular quadrilaterals and kites. The second, trapezoids and isosceles trapezoids. And in the third, we'll look at parallelograms, along with special parallelograms. I will also refer to this initial screen right here with the Venn diagram to start each video, and we'll practice a few conditional statements as we go. Alright, our Venn diagram. We can see that our entire field here is representing quadrilaterals. Quadrilateral is a shape with 4 sides. It also has 4 interior angles and 4 exterior angles. So when we have this different collection of subsets, we get more specific the further we go inside. So in the subset of parallelograms, we have 3 different types of parallelograms. We have a rhombus, a rectangle, and then a square, which is the intersection of rhombus and rectangle. So it would have properties of both of those. Totally separate subsets are trapezoids and kites, which do not share any properties with any of the other subsets of quadrilaterals. So when we're forming a conditional statement using a Venn diagram, if we start inside and go out for our hypothesis, conclusion, or if-then statement, like for instance, let's look at this first one. If a shape is a square, then it is a parallelogram. So this would be a case where we are going inside out. If a shape is a square, then it is also a parallelogram. We started in, moved out. That will always be true. Let's look at a second conditional. If a shape is a parallelogram, then it is a rectangle. In this case, parallelogram is further outside, and we would be going further inside for our hypothesis conclusion. If a parallelogram, then a rectangle. This could be true. Sometimes will be true, which means false. In order for a conditional to be true, it has to always be true. So anytime we get a sometimes true answer, we're not really using that. We consider it to be false. Alright, the next slide, we're really staying out here in this region where we're not getting into any of these specific subsets of quadrilaterals. What we're looking at is something that in some books might be called a trapezium. It's really the American definition. And because the English definition is a little different for trapezium, I'm just going to call it an irregular quadrilateral. So that means the side lengths might all be different. The angles and the interior also might all be different. So one thing about naming these quadrilaterals is it's important that you name using 4 vertices. So this would be quadrilateral A, B, C, D. What would be an incorrect name for this quadrilateral? Well, if I jumped across a diagonal and called this ACBD, that would be incorrect. Consecutive sides, you'll hear me mention and you'll see mentioned in textbooks a lot of times. Consecutive sides could be DC and DA. It means they're next to each other. Or we could say DA and AB are consecutive sides. Or AB and BC are consecutive sides. What are consecutive angles? Those would be angles that are next to each other as we travel around the perimeter. So angle D and angle A are consecutive angles. We could also say angle D and angle C are consecutive angles. Opposite sides, you would have to travel across, so BC and AD would be opposite sides, as would AB and DC. These would also be considered opposite sides. And our last vocabulary for general quadrilaterals are opposite angles. This would be traveling across a diagonal. So angle D and angle B are opposite angles, as well as angle C and angle A. Let's take a look at kites. Here's a definition of a kite. A kite is a quadrilateral with exactly 2 pairs of congruent consecutive sides. On our Venn diagram, kites are a subset that are really off on their own. A kite is never a trapezoid, and a kite is never a parallelogram. let's look at the two pairs of congruent consecutive sides. This would be one pair, and this would be our second pair. Sometimes when you're thinking about the kite, you could envision the kind of kite that, maybe you built a frame out of wood and you tied a string to it, and the string came down to some happy little person who's flying their kite. And we would sometimes think of, maybe it has a tail. We sometimes think of this as the top of the kite and the bottom of the kite, if you think of it as what it would look like if it were flying. Those we would also consider the vertex angles, which are not necessarily congruent to each other. But for the purpose of, look at the kite in a way that we're all kind of familiar with, let's refer to the top and bottom angles as the vertex angles. So this is a vertex angle, and this is a vertex angle. And so these ones on the side I would call non-vertex angles. Okay, and there they are marked differently, and they are not necessarily congruent. The non-vertex angles, the ones on the side, are always congruent in a kite. Diagonals of a kite are always perpendicular. And the diagonal connecting the vertex angles always bisects the other diagonal. So here are a couple questions about kites. If we look at the diagonals constructed in any kite, how many pairs of congruent right triangles can we prove? Well, we have all four of these are 90. So I do see 4 right triangles. Because of our congruence marks, this is a hypotenuse, leg. So we can say these 2 right triangles are congruent. And by the same triangle congruence shortcut of hypotenuse, leg, we can also say that these 2 right triangles are congruent. How many isosceles triangles are formed once diagonals are constructed? Well, we get one isosceles triangle right here, where I could prove base angles are congruent. And there is a second isosceles triangle right here, there we go, where we could now prove that these base angles are congruent. Stay tuned, 2 more videos coming up.